Okay, section 10.2, regression. It's a continuation of section 10.1. If you look at the section 10.1, we try to find the correlation coefficient, linear correlation coefficient. If there is a correlation, then you can always find the correlation coefficient here, like here, the value of R, as you can see. If R is exactly 1, that means the data sets are highly correlated. That means here we're talking about the linear correlation, meaning most of the data they are around some line. Okay, as you can see here, first and second, the linear correlation coefficient is almost equal to 1 or -1, so they are highly correlated. So section 10.2 is regression. Regression means this line, we would like to find the equation of this line. That's the regression. Okay, so to understand the section 10.2, you also have to understand section 10.1. So our goal is to find a regression line. Okay, and then eventually we're going to talk about a couple of things like marginal change, inflection point, residual points as a tool for analyzing the correlation results. So this is the equation we use as a regression equation. This equation represents the equation of a line. If there is a correlation between x and y, then we can use this equation to predict the value of y for any given value of x. So here x is the independent value and then y is the dependent variable. Okay, so think about there is a data set of let's say you have a data set, x is time and y is let's say price, let's say, and they are linearly correlated. They are linearly correlated. X means time and y is the price. And if they are linearly correlated, we would like to find out this line where this y cap represents the value of y, prediction for the value of y for any value of x. Let's say if x is 1 and y is 2, x is 2, y is 3, x is 3, y is 4, something like that. What is the value of y when x is 100? We would like to make that prediction, and that can be denoted by this y cap. This line, this equation is called regression equation. Okay, that's the regression equation. And a couple of symbols you have to be familiar with. If you are using sample, these are the notation. For this b0 represents the y-intercept of the line, and b1 represents the slope. Slope means rate of change, how the line is changing, and this y-intercept means when, at what point the line intersect with the x-axis. And this is for the sample, this column, and this column is for the whole population. Okay, so there are some of the requirements when we try to find the regression line, and these requirements are very similar to the section 10.1. The sample value is supposed to be simple random, like x values and y value, and whenever we try to plot the scatter plot, we should make sure that there is a clear visualization of line. And we know that for this type of linear relation, the outliers plays very huge role, a strong effect. Okay, and yeah, this is also one of the requirement from section 10.1. Here are two different requirements from in this section. For the different fixed value of x, the distribution of the corresponding value of y values all have the same standard deviation. So that's supposed to be the one of the requirement. And another one is for different fixed value of x, the distribution of the corresponding y values have means that lie along the same straight line. So these are the requirements whenever we try to find the regression line. And let's say the standard deviation for the y values and the standard deviation for the x value for the sample, then we can find the slope by using this formula. b1 is r times standard deviation for the y values divided by standard deviation of x value. And if you would like to find the y-intercept, you need this mean of the y minus the the slope times mean of the x. Most of the time we are going to use StatCrunch for finding this information. Okay, there is a rounding Well, most, normally we round these values to the three decimal place, but do not worry, just follow the instruction you have given in your MyLab. Whatever they ask you to round, just use that. And using this regression line, if you can predict the value of y more correctly for any value of x, then that's the good model. If you cannot predict, more correctly, that's called the bad model. So good model and bad model. So use the for the correlation, use the regression equation for prediction only if the linear correlation coefficient r indicates that there is a linear correlation between two variables. Meaning, let's say if your linear correlation r is 0.05, that means it's too low, so that means it's not highly correlated. Okay, and then to make the prediction for the scope, use the regression line for prediction only if the data do not go much beyond the scope of the available sample data. Okay, so you have the sample data and you would like to make the prediction which is very far from the sample data. What does that mean is, let's say this is the sample data we're talking, and we have the data up to 3, and we would like to make the prediction for very, 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 very far time. Then do not use this prediction model, because that might not give you the accurate value. Okay, so when do you predict? When do you use this prediction thing? Here is the one strategy for predicting value of y. Is the regression equation a good model to predict? And you need to answer these 3 bullets. The regression line graphed in the scatter plot shows the line fits the points well. R indicates there is a linear correlation. R means the coefficient of correlation, which we found in section 10.1. The prediction is not much beyond the scope of the available data. If the answer for all 3 questions is yes, then we can use the regression, this equation, to predict the value. The answer is no, then instead of using the regression, we just use a sample mean for the value of y. Okay, here is a marginal change. What is marginal change? Marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. So if you go back and look at the regression line, here you see the b1, which is the slope of the line. The slope b1 in the regression line represents the marginal change in y that occurs when x changes by just 1 unit. So when you change x by 1 unit, whatever change happens in y, that can be represented by b1, that's called marginal change. For example, let's say this y cap equal negative 10.9 plus 0.174x. That represents what is that? Number of tickets in jackpot. And then x represents y represents the number of jackpot. So jackpot versus ticket. So x represents the ticket, y represents the jackpot, and the number of jackpots is in million. The unit is million. So this 0.174 is in million. Million means if you multiply this by 1 million, it would be 174,000. So this is, which is actually the slope of this line. If you raise the value of x by 1 unit, remember 1 unit for this example is 1 million. If you raise the value of x by 1 unit, which is okay, so x is the jackpot, and then y is the number of tickets. So if you increase the value of jackpot by 1 million, then that means you have to sell 174,000 tickets. That's the meaning of this marginal change. Okay, you might have outliers in data. We already know the meaning of the outliers, and that might influence your regression line hugely. And then after that, you have influential points, which are points that strongly affect the graph of the regression line. You have to be careful with these influential points. And then there is one more word that's called residual. Residual means whatever you observe and whatever you predict from the regression line. So if you have observed value and you do the prediction, and if there is a difference, that's called residual. Okay, for example, this is the data between x and y, and we somehow found this regression line y cap equal 1 plus x. As you can see here, the observed value of y for x equal 8 is 4. But if we use this line, if x is 4, the y value would be 5. You see there is a difference. 8 and 5, sorry, 4 and 5. When x is 8, the value of y is supposed to be 9 from the prediction, but the value of y here given is 4. So there is a difference, 4 minus 9. This difference is called residual. That's all. So now, using this information, we're going to see a couple of examples. Let me start with number 1. Here is the problem. Using the weights in pound and highway fuel consumption amounts mile per gallon of 48 cars. So 48 cars, here is the weight and here is the fuel consumption, and there are 48 different cars. This is the regression line we found. How did we find? I'm going to show you that in the next problem, or maybe I can just use this data. To find this regression line, you have to open the data in StatCrunch the way we did in section 10.1. Go to the stat, go to the regression, and choose simple linear. The first variable is weight, the second variable is highway fuel consumption, and if you just hit compute, the equation on the top here, this equation is the regression equation. If you want to express this in terms of x and y, just replace this by x and this by y, and then go back and do the same thing. Choose x and y, and then if you hit compute, you get this equation of line. That's the regression line. You will get this regression line on the top of the page. Look at here. Instead of y, they are using y cap. Everything else is same. 58.9 if you round it to the one decimal place, and 0.00749. So that's the same regression line. Okay, but in this problem it's given. Now we just have to answer the question, what does the symbol y cap represents? So y cap represents the predict value of highway fuel consumption. Y cap represents actual value of high fuel consumption. Y cap represents actual value of weight. So keep in mind, if you click here, this is x and this is y. So y means highway fuel consumption. So y cap represents a predicted value. This is the prediction, and that's the regression line. So now, based on this prediction, we need to find out what are the specific value of the slope and y-intercept of the regression line. Remember, the number in front of x with the sign, that's the slope, and the individual number only itself here, that's the y-intercept. So negative 0.00749 is the slope, and then 58.9 is your y-intercept. What is the predictor variable? What is the predictor variable? So the predictor variable is the weight, which is represented by x. The predictor variable is weight, which is represented by y. Remember, y itself is the highway fuel consumption. X is your the independent variable. If you go back and check your notes, you are going to find, go back to this one. X is also called explanatory variable, predictor variable, or independent variable, whereas y is a response variable, dependent variable. So now, based on that information, we can say that x is predictor variable, which is weight. The predictor variable is weight, which is represented by x. Assuming that there is a significant linear correlation between weight and highway fuel consumption, what is the best predictor value for a car that weighs 2,986 pounds? So this is your predicted, and then x, if the weight of the car is 2,986, you just replace this x by this and use the calculator. So where is the calculator? Yes, so go and type this number 2,986 86 and multiply that by this negative 0.007. So multiply that by 0.007 49, but make it negative. Okay, here is the plus minus sign, and then if you multiply, this is the number you are going to get, and plus 58.9 plus 50, sorry 58.9. Okay, I made the mistake. First of all, it's not cancel, it's a CE. So here's the thing, 0.00749 negative times the weight is 2986. If you multiply that and add 58.9, this is your prediction. So the best predicted value of highway fuel consumption, if you round it to the one decimal place, it's a 36.5. 0.5. You see, 36.5. That's our prediction. Okay, let's go to the next question. You have given this scatter plot. From this scatter plot, you can find the data. If you just open this, as you can see here, for the x value 2, the y value is 9. For x value 5, the y values, there are 3 y values, 2, 3, 4. You have to write it down in your StatCrunch. Go to the StatCrunch and then type these values here. Just name them x and then y. And when, as you can see here, 5, 6, 7, 5, 5, 5, 6, 6, 6, 7, 7, 7, repeat it. And there is one value at 2. So at 5, it's if you zoom in at 5, the value is 2, 3, and 4. So 2, 3, and 4. So I will go back here, type it 2, 3, 4, 2, 3, 4, 2, 3, 4, and then for the 2, it's 9. So this is the data. You go to the stat, you go to the regression, you choose the simple linear, you choose your x value and then y variable, and if you hit compute, the top line here, that's the regression line. Don't be confused, it gives you, the StatCrunch gives you as a y, not y cap, but if you want to change it to the y cap, you just have to do this, what is that? You just have to go back to the notation and you can change it to the anything, y cap. You know, I don't have the cap. Let me see. Can I choose the cap? No, there is no cap. That's why I just have to use, yeah, I don't see the cap sign on my keyboard. So I'm going to use, you know, the y value. So regression, simple linear, x, and then y, and hit compute. So this equation, just copy it here. It's a 9.5, round to the 3 decimal place, 9.529. 9.529, that's our y-intercept. And then where is that? The slope is negative 1.059. Negative 1.059. Remember, it says round to the 3 decimal place. So that's our regression line. What is the equation of regression line for the set of 9 points? So now part B is remove 2, 9 from the data. So you have to go back to your data. You have to cancel that. You have to remove this 2 and 9. That's the reason I put this 2 and 9 at the bottom, so that it would be easier for me to remove, and go back again and do the very same thing by choosing x and y. Now this time the regression line is y equal to 3. If you don't have this point, y equal to 3 represents most of the data. So y equal 3 is our regression line. Okay, so next question is compare the part A and B. As you can see here, part A and B, there is a huge difference because of one influential data. So regression line changes, there is no, the removal of the point has a significant impact. So part, this one is the right option. Okay, Let's go to the next question. I will do question number 10. Question number 10, you have given data. Listed below are the foot lengths and heights of males. Find the regression equation, letting foot length be the predictor, x, foot length is x. Find the best predicted height of the male with the foot length 273.1 millimeter. So first of all, open the data in your StatCrunch, and then after that, foot length is x and then height is y. That's we supposed to do according to the problem. Go to the regression, use a simple linear, choose your x, choose your y, and hit compute. This is your equation, regression line. So what is the regression line? Round the y-intercept to the nearest integer. So it's a 359. You have to read the instruction very carefully, because sometimes they are asking round it to the nearest integer, sometimes 3 decimal. Round the slope to the 2 decimal place. If you go back to the problem, the slope is 5.18. 5.18, that's the slope. So that's the regression line. Now the best predicted height of a male with the foot length 273.1. Just use this equation, replace this x by 273.1 and do the calculation. So what you can do is you start with the 5.18, that's the slope, times 273.1, hit equal, plus the y-intercept, which is 359. That is the height, that is the prediction for the height, and they are asking us to round it to the nearest integer, so it's 1774. 1774, that's the prediction. Now how does the result compare to the actual height? So check your data, the actual data. What is the height for what is that? What is the height for 273? So find out the 273. Is there 273 here? 274 is there. Let me just sort the table. 274.2 is approximately 1788, and now we would like to predict for 273, which is close to this value. So it's supposed to be less than 1788. So it looks very close. The result is close to the actual height of 1776 millimeter, right? Okay, now those are the type of the problem you have to do. Let's do some checkup here. Give a collection of the pure sample data. Given a collection of pure sample data, the regression equation, this is the regression equation. Okay, in a scatter plot is a point lying far away from the data points. It's an outlier. They are far away from the data line. Pure sample data may include one or more blank, which are points that strongly affect that's influential points. Okay.